Okay, so I'd like to welcome everyone back to the QFI seminars. So today we have a very special speaker, Professor Ian Affleck from University of British Columbia. So Professor Affleck is one of those professors who really doesn't need an introduction, but I think I'll attempt it. So Professor Affleck got his bachelor's from Trent University, Ontario from 1975, his master's from Harvard in 1976, and his PhD in Harvard in 1979 under Sidney Coleman. He was a junior fellow at the Harvard Society of Fellows from 1979 to 1981. And from 1981 to 1987, he was an assistant professor at Princeton University. And he's been a professor at University of British Columbia from 1987 to 2003. And he's been a University Killam professor at University of British Columbia from 2003 to present. He was also a professor at BU from 2001 to 2003. He was a researcher at the Saclay Nuclear Research Center in France from 1984 to 1985, and he was a researcher at the Institute for Theoretical Physics in Santa Barbara, California from 1999 to 2000. He's the recipient of numerous awards, including, but definitely not limited to, the Governor General's Medal in 1975, the Sloan Foundation Fellow from 1983 to 1987. He is currently the Fellow of the Canadian Institute for Advanced Research. He has been the recipient of the Herzberg Medal, the Rutherford Medal, the Onsager Prize, the Bruckhaus Medal. He is a fellow of the American Physical Society, and since 2010, he has been a fellow of the Royal Society. In 2006, he won the CAT Medal for a lifetime achievement in physics. So please help me in welcoming either by unmuting yourselves or virtually Professor Ian Affleck.
Thanks for the flattering invitation and introduction, Jonah. So I want to talk today about models of interacting Majorana fermions, which can exist in condensed matter systems and exhibit some fascinating phase diagrams, including supersymmetry at some critical points. This is a project I've worked on for about 5 years. Collaborators include Armin Ramani, who's now a professor at University of Western Washington, Marcel Franz, my colleague at UBC, Dima Pekulin, who's now at Microsoft Station Q, and Tarun and Kyle, who are my graduate students, and Xiaoyu Zhu, who was a visitor from China. So here's an outline of the talk. I'm going to introduce the motivation and the model. Then I want to talk about the one-dimensional case where we really nailed what happens. And then I want to talk about the square lattice case and the triangular lattice case, where we have some mean field predictions and some field theory predictions, and we've also done some DMRG calculations, but just on relatively small ladders at this point. So I think there's still open questions about these two-dimensional cases. Okay, so motivation and model. So it's predicted that if we have a strong topological insulator, and then we have a superconducting layer on top, we apply a magnetic field, so we get a vortex lattice. It's predicted that the effect of the topological insulator is to produce a Majorana mode at the core of every vortex. So Majorana fermions are candidates for qubits, and there's been a lot of interest in them over the years. It's been, for example, the main focus of research at Microsoft Station Q for many years. Charlie Marcus, who was at Harvard, moved to Niels Bohr Institute, is one of the leading experimentalists in this field. Various experimentalists have claimed to see Majorana fermions, but this has remained controversial. Interaction effects involving Majorana fermions have not yet been studied experimentally, but at least 2 experimental groups are interested in studying them to test our theoretical predictions. So Majorana mode is located near the center of each superconducting vortex. Majorana modes can tunnel between vortices, interact with each other with short-range interactions that scale like the exponential of minus the distance divided by the superconducting coherence length. And rather amazingly, the tunneling amplitude goes to 0 if the gate chemical potential of the topological insulator is tuned to a special value. We've studied the simplest possible version of this model with shortest possible range interactions. We're calling it the Majorana Hubbard model. So it has a hopping amplitude T, has interactions G. And we studied both signs of G over T because since we're sitting on top of a superconductor, it's not completely obvious if the interactions might be effectively attractive or repulsive. So far we've looked at the one-dimensional case, two-dimensional square lattice ladders, triangular lattice case, and also triangular lattice ladders. So let me start with the one-dimensional case. So here's the Hamiltonian. So gammas are Majorana Fermions, so they're Hermitian. Gamma j dagger equals gamma j, and they have standard anti-commutation relations. So we have a nearest neighbor hopping term, and we have a four-site interaction term. Notice the interactions have to be in four sites, not one or two sites. And this is because gamma squared on a given site is 1. So we have to have four sites to have a non-trivial interaction. So this model has no conserved particle number, basically because of the fact that the gamma j's are Hermitian, but it does have some important discrete symmetries. And this one-dimensional model can be studied by field theory and DMRG methods, as well as mean field theory, which turns out to be quite effective. So it turns out that Majoranas like to pair up and form complex Dirac fermions. So we can always combine a pair of Majoranas to make a Dirac fermion or a complex fermion. So for example, if we combine the Majoranas in site 2j and site 2j plus 1 to define a Dirac fermion Cj, then we can easily check that I gamma 2j plus 1 is twice C dagger j Cj minus 1. So it has eigenvalues plus or minus 1. So, but notice the way we pair up the Majoranas is an arbitrary choice. We could combine 2j with 2j plus 1, or we could combine 2j minus 1 with 2j. If you make this combination, or actually either combination, then half the interaction terms become very simple. Become simply minus g times this interaction, which looks like a nearest neighbor interaction for ordinary spinless Dirac fermions. Notice that because of this factor of I, which gets squared, we get a sign change. So perhaps a bit confusingly, positive g actually corresponds to attractive interactions, and negative g corresponds to repulsive interactions. There's no conserved charge, so the mean field density is determined by the interactions. So the density is not something we can control, but the interactions will control it. So for the positive g case, there's two mean field ground states for positive g corresponding to attractive interactions. So we can pair up pairs of Majoranas to make Dirac fermions. And then due to this interaction for positive g, and also using the fact that t is positive, we have the same filling factor on neighboring sites. And for positive t, this will correspond to vacant sites. So we could pair up pairs of Majoranas to make Diracs, and these sites are vacant. But there's two ways of doing this, because we can pair up 2j and 2j plus 1, or we can pair up 2j minus 1 and 2j. So this leads to two different ground states at the mean field level. We can rewrite the full Hamiltonian in the complex fermion basis. So let's combine for convenience define pj to be 2c dagger j cj minus 1, eigenvalues plus or minus 1. So then the hopping term has a simple term that just involves t times pj, and then it has a complicated term that involves hopping and pairing. And if you look at the interaction terms, there's a simple pj plus 1 term. There's also a complicated term involving 3 sites, which involves hopping and pairing. It also depends on the sign of pj plus 1. So if we only keep the first t term and the first g term, that's the mean field theory. And remarkably, this mean field theory turns out to be qualitatively correct at large g, for either sign of g, actually. So if we go to negative g, now there are actually 4 mean field ground states, because now we get basically we get filled an empty filled. So it's like a charge density wave. And so there's 2 states if we combine the Majoranas this way, also 2 states if we combine them this way. So altogether we have 4 mean field ground states for negative g, which corresponds to repulsive interactions. That's why we get this particle hole type state. or charge density wave. So we verified that these phases actually occur at strong coupling using DMRG calculations. So the non-interacting model we can solve by Fourier transforming. So we can define a Fourier transform gamma k involving a sum over all sites, gamma j e to the ikj. But notice that while gamma j is Hermitian, gamma k is not Hermitian. But gamma k does have the feature that gamma minus k equals gamma k dagger. So the feature of Majorana fermions when we go to k space is that we can restrict ourselves to positive k. So the Hamiltonian, non-interacting Hamiltonian can be easily diagonalized and takes the following form: gamma k dagger, gamma k sine k, with k restricted to 0 to pi. So, oops, sorry. So that's what the dispersion relation looks like. So notice that all states are empty in the ground state. We simply have no fermions present, unlike with Dirac fermions where we would fill up half the Fermi C, half filling. And notice that they're only particle excitations, not whole excitations. That's the signature of Majorana fermions. Also notice that the low energy excitations have linear dispersion, so it looks relativistic. So the low energy effective Hamiltonian corresponds to relativistic Majorana fermions. So we can define gamma j to be gamma r plus minus 1 to the j gamma l, right and left movers. So we can see from this picture, so this is near wave vector 0, this is near wave vector pi. And then the low energy Hamiltonian is the relativistic non-interacting Majorana fermion model involving gamma right dx gamma right minus gamma left dx gamma left, where the velocity is 4 times t. These operators have scaling dimension 1/2, so h has the expected dimension of 1. Now, if we look at the lowest dimension interaction in the continuum model, because gamma r squared is proportional to 1 and gamma l squared is proportional to 1, we have to put in derivatives. So this is the lowest dimension interaction we can write down. And because it involves 2 derivatives and 4 fermions, it has dimension 4. So this is highly irrelevant at weak coupling. So we expect to get a free Majorana fermion model with some modified dispersion, at least for small enough g. At sufficiently large g, we find broken symmetry phases predicted by mean field theory. Remarkably, the transition occurs at incredibly large positive g at g of 256. Whereas for negative g, we get a transition at g equals -3. So there's a very strong difference between positive and negative g. So the fact that the critical g is so large for positive g made numerics extremely challenging. So because we're in basically a non-interacting phase up to g of 256, correlation length is infinite. Now it gradually comes down from infinity as we go beyond g of 256, but it's perhaps still a few hundred lattice sites at g equals infinity. So that made the numerics very challenging, but DMRG was able to actually study this nonetheless, thanks to some brilliant calculations by Armin Romani. So the nature of the second order phase transition for g equals 256 is interesting. So the critical line with g less than 256 corresponds to the one-dimensional quantumizing model at the critical point h equals 1. As you may know, the quantum one-dimensionalizing model corresponds to a Majorana fermion, relativistic Majorana fermion. There's an interesting symmetry that keeps the model critical. This is translation by one site. So this symmetry takes gamma right to minus gamma right. It forbids the mass term m times gamma right, gamma left. Corresponding symmetry.
Sorry, can I quickly ask a very quick question?
Yes.
So on the previous slide, this model seems to have some kind of correspondence to the transverse field model, right? So
yes, that's right. Yeah.
What role does G play? So in short, my question is like there are 2 phase transitions that occur, but in the transverse field there's only one that occurs. So
yeah, G basically you can think of as varying H, essentially.
So when you vary H, there's only one transition in the Ising model, but there seem to be 2 there.
But it turns out that basically H is sort of fixed at 1 by symmetries. So as you vary G, H doesn't change, it stays at 1 up to the critical G. So I guess there's a coupling constant in front, which I've haven't bothered to write down. This will change with G, but one stays at the Ising critical point. And we can understand that because, well, there's a mass term that would put us into a gap phase, but this involves m gamma right, gamma left. And there's a symmetry of translation by one site, which as you can see from the previous formula here, translation by one site changes the sign, actually, I guess changes the sign of gamma left. So this forbids a gamma right, gamma left term. So the mass term is forbidden by symmetry. And it's interesting to say, well, what is the symmetry that corresponds to this symmetry in the Ising model? And this turns out to be Kramer's Wanier duality. So it's a symmetry that takes h minus 1 to minus h minus 1, where h near 1. So it switches the broken and unbroken symmetry phases. So it's this Kramer's Wanier symmetry in the Ising model that corresponds to this translation symmetry in our Majorana model. Does that answer your question?
No, I'm still not quite sure. Is it that G here plays the role of something combined with the exchange and also the transverse
I
field?
think G, you can think of G as corresponding to just changing simultaneously both of these coupling constants so that the ratio stays 1.
Okay. Thank you.
Changes the velocity. Yeah. Okay. So okay. So the Ising transition is a second order in the ordinary Ising model, but it becomes first order if we insert a high enough density of randomly located vacancies. And this transition can be realized by using s equals 1 spins instead of spin a half, inserting an SZ squared term, which favors SZ, I guess I say in American, SZ equals 0. So this is the corresponding Hamiltonian that exhibits both the second order and first order transition. So this parameter delta, if delta is positive, it favors SZ equals 0. If delta is 0 or negative, it favors SZ equals plus or minus 1. So if delta is small enough, SZ is plus or minus 1. And now we basically just have the standard spin a half Ising model, and we have the second order transition. But if delta is large enough, it favors SZ equals 0. Then we have a kind of a trivial phase. And this kind of a trivial phase transition at gamma equals 0, where we just flip from SC being plus or minus 1 to SC being 0. And it turns out that if we move along this critical line, there's a special tricritical point where the transition changes from being second order along the blue line to first order along the dashed green line. This may be not too surprising, this transition is first order because it's kind of trivially first order along this gamma equals 0 line. And it turns out that this there's a critical point which separates the second order line from the first order line. And this is a conformal field theory, which is a supersymmetric. Also turns out that for G slightly bigger than this critical point, the only interactions we can write down that destroy the symmetry of the critical point actually preserve supersymmetry. So we expect that there's a region for G slightly bigger than 256, which is massive, but is still supersymmetric. So we predict massive fermions and bosons with equal mass. So this is quite surprising from the point of view of the model, because the original model only involved fermions. So if we get bosons appearing, there's some kind of fermionic bound states. And supersymmetry actually requires that the bound states have the same energy gap as the fermions. So a remarkable result of supersymmetry. Okay, any questions about the one-dimensional case, or can I move on to 2 dimensions? Okay.
I'm sorry, may I ask a quick one about the 1D case?
Yes.
Is there an easy way of understanding why the critical G on the positive side is so much larger than the critical G on the negative side?
There was a paper which tried to explain that. It was kind of a technical explanation. but it's worth mentioning that if we just slightly modify this model, the critical G moves down to a much more reasonable value. And this was done by O'Brien and Fendley in Oxford. So it turns out that if instead of having interactions on site 1, 2, 3, 4, you have interactions on site 1, 2, 4, 5, and then 2, 3, 5, 6, etc. So 2J, 2J plus 1, 2J plus 2, 2J plus 3, you have the same phase diagram, but the phase transition moves down to values of G around 2 or 3. So it's kind of an artifact of having interactions on site 1, 2, 3, 4 that leads to this absurdly large critical G. And you can move it down to much more reasonable values by just slightly modifying the interactions. And there's some sort of explanation of this, but I don't remember the details. There was a paper that tried to explain this, but it's kind of a detailed explanation. Good question.
Very interesting. Thank you.
Yeah. Okay, so now I want to move on to the two-dimensional square lattice case. I haven't told you about the negative G one-dimensional case. If I have time at the end of my seminar, I'll come back to that. But let's now move on to two-dimensional square lattice case. So this is the Hamiltonian. So square lattice looks a bit unrealistic because usually a vortex lattice is triangular. So I'll come to the triangular case a bit later on. But there are a few superconductors that actually have a square vortex lattice. So this is not completely unrealistic. And it turns out that the square lattice case looks like it has a more interesting phase diagram than the triangular case. So this is a model we consider on the square lattice. So we have nearest neighbor hopping. And we have the horizontal hopping has a sign change. So it has a different sign on even and odd sites. And I'll come back to the reason for that in a minute. The interactions we take to be on square plaquettes, so shortest possible range interactions. And we also consider a second neighbor hopping term, which has the following form. Oops. Okay. So you might ask, well, why do we have this alternating hopping term? And the reason is that we do have a requirement that we have one flux quantum per plaquette, because this is supposed to describe a vortex lattice. And this actually requires this sign change. We could make some gauge transformations that would move the sign somewhere else, but we can't avoid having some sort of non-trivial sign in the hopping term. And this has interesting effects on the physics, as we will see. The T2 term breaks time reversal symmetry and parity symmetry and changes the phase diagram significantly. So I'll discuss both the T2 equals 0 case and also the T2 non-zero case. So the phases are again characterized by spontaneously broken symmetries. So now it's important to ask, well, what are the symmetries of the Hamiltonian which make it broken? So we have translation by one site in the X or Y model. Translation in the Y model, Y direction, also involves putting in some sign changes in the Majorana Fermions, which we can do. We also have pi/2 rotation symmetry. If T2 is 0, we also have time reversal symmetry, and I'll define that precisely a bit later, and also parity or spatial reflection symmetry. It turns out that even if T2 is non-zero, we have PT, a product of time reversal and parity. In addition to these exact lattice symmetries, there are some emergent symmetries in the low energy effective field theory. So these pairing phases break rotational symmetry as well as parity symmetry for T2 equals 0 and translation symmetry. So again, if we have positive G, then we get so-called ferromagnetic phase. So again, pairs of Majoranas like to pair up and form Diracs. And now they can do it this way, or they can do it this way. So there's two states where we form vertical dimers, but then we have two other states where we form horizontal dimers. So altogether we have 4 ground states. And these would be the favored states at a mean field level for positive G. For negative G, again, we get this charge density wave because we have effectively repulsive interactions. And now we actually get 8 states because we can form this charge density wave. We can translate by 1, or we can shift by one site the vertical direction to pair up Majoranas a different way, or we can rotate by pi/2. So altogether, we now have 8 ground states for negative G corresponding to repulsive interactions. So these pairing phases break rotational symmetry and parity symmetry for T2 equals 0, and also time reversal. Now I'll define precisely what time reversal is. So it takes I to minus I to n to unitary. Also takes gamma mn to minus 1 to the n plus n gamma mn. And this can be seen to be a symmetry of the nearest neighbor hopping term because every nearest neighbor pair, one of the gammas changes signs, and that compensates for I going to minus I. But if we have second neighbor hopping, this breaks time reversal because neither of these gammas, both these gammas either don't change sign or both change sign, and I goes to minus I. So time reversal is broken with second neighbor hopping. The interaction term preserves time reversal. Okay, so we can also take a field theory normalization group approach to study the nature of the critical point. So if you take a non-interacting model, we can solve exactly. And this is the dispersion relation in terms of kx and ky. So for T2 equals 0, we just have sine kx squared and sine ky squared. For T2 non-zero, we also have these cosine kx times cosine ky squared terms. The Brillouin zone can be restricted to kx between 0 and pi, and ky between minus pi over 2 and pi over 2. You might ask, why this strange Brillouin zone? Well, this restriction is basically because of the fact that we have 2 sites per unit cell because of the sign change in the hopping term, horizontal hopping term as we go in the vertical direction. And then we can cut our Brillouin zone in half, again, as we did in one dimension, because we're dealing with Majorana Fermions. So when we Fourier transform, we can restrict ourselves to half of the Brillouin zone because gamma k equals gamma minus k, where k is now a vector. So if T2 is much less than T, we have low energy excitations near 2 points in K space, 0, 0, and pi 0, where we have Lorentz invariant dispersion. So it looks like the following dispersion relation, or if T2 is 0, we have linear dispersion, so gapless fermions. And it turns out that this is Lorentz invariant. So these two valleys look a bit like graphene, but we're dealing with Majorana modes, not complex fermions as occurs in graphene. So low energy field theory has 2 species of 2-component Majorana fermions. This occurs basically because we get a doubling because of the broken translation symmetry, and we get 2 points in K space where we have gapless modes. So we can actually combine these into 2 complex fermions, which we can combine to make a 2-component complex fermion, which actually is Lorentz invariant. So psi here is a 2-component complex fermion, and the low energy Lagrangian is actually Lorentz invariant. So these are the gamma matrices. Sorry, my phone is ringing, but you don't hear it. So we have the gamma matrices, which are Lorentz invariant. This is the usual Lorentz invariant term, non-interacting term, and this is the mass term that's present if T2 is 0. And we also have a interaction term, which is also Lorentz invariant, involving no derivatives. And I've set V equals 1 here for convenience. And psi bar is psi dagger gamma 0. Okay, so this is interesting because not only do we have emergent Lorentz invariance, we also have emergent U1 symmetry, because this preserves the U1 symmetry. So it turns out that the U1 symmetry is not exact. There's a higher dimension term which actually breaks the U1 symmetry. I'll come back to a little bit later. But it turns out to be irrelevant at the critical point. So it turns out that even this interaction is irrelevant in the RG sense, because in 2 + 1 dimension, psi has dimension 1. So psi bar psi squared has dimension 4. And 3 is the marginal interaction dimension in 2 + 1 dimensions, so that this interaction is irrelevant. And therefore, we expect to have this gapless relativistic fermion phase for a small enough G, similar to what happened in 1 dimension. So it's also interesting to look at this interaction. We can write it 2 different ways. And we see that basically for a negative G, this is an attractive pairing interaction. And for strong enough, for positive G rather, this is an attractive pairing interaction. So for strong enough positive G, we expect to get a transition into a UN breaking phase where psi 2, psi 1 gets an expectation value. And this will correspond to breaking, so pairing up Majoranas to form pairs, which corresponds to a ferromagnetic pairing transition, or corresponds to a superfluid phase in the fermion notation. So for positive G, we're predicting a superfluid transition into a paired phase. And this corresponds to the ferromagnetic phase that we predict in the Majorana basis. So for T2 equals 0, the fermions are massless in the G less than G critical phase. At the superfluid transition, we get a massless Goldstone boson, as well as massless fermions. So this suggests this transition might be supersymmetric, because normally at a superfluid transition, we just have a Goldstone boson, but the fermions are massive. But in this case, the fermions are massless at the critical point, as well as having a Goldstone boson. So we have massless fermions and bosons, and this suggests that the model is supersymmetric. So this will happen when T2 is 0. So this supersymmetric model has been studied before in condensed matter physics, but it's remarkable here that the UN symmetry is emergent, not exact. Non-zero T2 gives the fermions a mass. Now the superfluid transition is the usual UN breaking 2 + 1 dimensional universality class, or basically Wilson-Fisher universality class. There is a UN breaking term in the effective Hamiltonian, this is it, but this now involves 4 fermions and 2 derivatives. So this is dimension 6, it's even more irrelevant than the non-derivative terms. So Kyle Waymer, my student, and I studied this interaction and showed that it remains irrelevant at the critical point using the epsilon expansion. Also interesting that we started with a lattice model, and we have a single relativistic fermion model, whereas the Nilsson-Onomiya theorem predicts that we always get 2 channels of Lorentz invariant fermions in low energy model. The reason we evade the Nilsson-Onomiya theorem is because the UN symmetry is broken in the lattice model, but it gets comes back in the field theory. So it's an interesting, might be an interesting approach for doing lattice simulations of field theories. So now I want to talk about results on ladders. So we studied 2- and 4-leg ladders using the square lattice geometry by a combination of analytic and DMRG methods. So it was difficult so far to go beyond the 4-leg ladder, but maybe ultimately people can go to 6 legs or 8 legs, but this has not been done so far. So it turns out in the 2-leg case, there's an exact UN symmetry. This can be seen by defining complex fermions. So we combine a pair of fermions on the 2 legs of the ladder, 0 and 1, to form a complex fermion. And we put in an alternating plus or minus I depending on which leg of the ladder we're on. So -1 to the m factor. Then the horizontal hopping term becomes 2it gamma c dagger m c 2m plus 1 minus emission conjugate. And the vertical hopping term becomes -1 to the m cm dagger cm. So both of these terms preserve UN symmetry. And the interaction term also preserves UN symmetry. So it's convenient to make a Jordan-Wigner transformation. And then the hopping terms become just the xy terms in the XXZ model. And the interaction term gives us a sigma z term. So now we predict the phase transition. So if G is small enough, we'll be in a gapless phase. If G gets up to 1/2, then we have a phase transition. Depending on the sign of G, we either go into any ferromagnetic ordered phase or a ferromagnetic ordered phase. And so for positive G, we actually get the antiferromagnetic phase, and for negative G, we get the ferromagnetic phase. But these actually map inversely into ferromagnetic, antiferromagnetic, because of this transition that we made, because of this -1 to the m factor. So for positive G bigger than 1/2, we get a ferromagnetic phase where we pair up Majoranas to make fermions, Dirac fermions, and we get this mean field ground state, which depends on the sign of T. And for negative G less than -1/2, we get this anti-ferromagnetic ground state, which corresponds to this state, where again now we have 2 ground states where we can shift this over by 1 unit. So we've actually confirmed our mean field theory exactly in the 2-leg ladder case by mapping onto a XXC spin chain. The 4-leg case is more complicated. There's no exact U1 symmetry. The model is not exactly solvable except in infinite coupling. So we analyze the model using DMRG. So to analyze the infinite coupling limit, we define complex fermions again. Now we can define a complex fermion on a leg, which now involves 4 Majorana fermions. So we combine gamma M0 and gamma M1 to make a complex fermion, gamma M2, gamma M3 to make a complex fermion. So now we have 2 complex fermions in every leg of our ladder. It can be seen that the interaction terms preserve the fermion parity in each rung. Unlike the horizontal hopping term, the vertical hopping term also preserves fermion parity. So number of fermions in each leg is fixed, but the horizontal hopping term breaks the fermion parity. At strong coupling, we can restrict ourselves to only 2 states with fixed fermion parity. So either we have 0 or 2 fermions in each leg, or we have 1 or 3 fermions in each leg. We can map these 2 states into the XY model with the Hamiltonian -2G sigma z plus sigma x, sigma x. This is the gapless XY, or in this case, XZ model. Unlike the 2-leg case, this model is gapless with no broken symmetry, except for fermion parity. Adding a small hopping term produces a gap. For small t over g, we can ignore horizontal hopping since it changes the fermion parity in each rung. This can be shown to increase the energy by amount of order g. On the other hand, vertical hopping just gives a perturbation which corresponds to like a magnetic field term. So we can map, including only vertical hopping, so only hopping on the ladders, we map it into an XY model with effectively a magnetic field. So this is what we get for odd fermion parity, we get sigma z and sigma z, and for even fermion parity, we get sigma x. And both of these are equivalent in this model. So for odd fermion parity, these lead to gap states with a spin ordering in the z or the x direction for even or odd fermion parity. For even fermion parity, this hopping term goes to sigma z. So the ferromagnetic order corresponds to Majorana fermions pairing up to form Dirac fermions. On the other hand, for odd fermion parity, we get sigma x, so we get the other mean field state. So even fermion parity corresponds to these Majorana states where we pair up the Majoranas to make Dirac fermions this way. Odd fermion parity corresponds to this mapping. So again, we've confirmed our mean field theory in the large coupling limit by mapping again into a XY model. So for g bigger than 0, we find only one transition. Mapping into complex fermions, ignoring interactions. We get one gapped complex fermion and one gapless complex fermion. With small g, we can integrate out the gap mode. Then we find unbreaking interactions are irrelevant. The UN preserving interactions are standard spinless electroliquid form. So we predict an umklapp term. Thus we predict a Kosterlitz-Salvas transition into a gap phase with sufficiently strong G. This agrees well with DMRG results. In the 2D limit, we expect this transition to become supersymmetric. So any questions about the 2-dimensional case? Okay, so let me move on to the triangular case, which is more relevant to experiments which normally have a triangular vortex lattice. So now again, we have some requirements in the hopping term required by having one flux quantum per plaquette. So now we have nearest neighbor hopping, but it turns out that this eta factor is plus or minus 1, and this is indicated by these arrows. Now, if we put in the shortest possible range interactions, we actually have 4 possible plaquettes. So we can have a plaquette like this. We can have a plaquette like this, or we can also have a plaquette like this. So these are the 4 shortest range types interactions we can write down. So we include all 3 of them. And again, symmetries require that these 3 be equal. So now if we solve the non-interacting case, it turns out that for nearest neighbor interactions, there's now there's no gapless modes. We have a gap between the upper and lower band. Now if we do mean field theory, it's quite interesting to compare it to the square lattice case. So square lattice case, we only had one type of plaquette, and the mean field theory gave the lowest possible energy for half of these plaquettes. And it turned out that doing a mean field analysis, it predicts this broken symmetry phase with strong enough coupling. On the other hand, in the triangular case, we have 3 different types of plaquettes. And if we, for example, pair up Majoranas on these sites and also these sites, we only lower the energy for 1/6 of the Majorana modes, or 1/6 of the interaction terms. So mean field theory doesn't predict Majorana pairing to form Dirac fermions. So we've done DMRG on the 4-leg ladder. Again, is consistent with not getting broken symmetries, even at strong coupling, consistent with the mean field picture. So I have some time left, so let me go over conclusions and then let me move on to tell you a bit more about the one-dimensional case. So the Majorana-Hubbard model on various lattices has rich phase diagrams. Majoranas like to pair up to form complex fermions for strong enough coupling. This breaks discrete symmetries, and supersymmetry can be realized in both 1 and 2 dimensions. So now let me come back to the one-dimensional case and tell you a bit more about the phase diagram. So far, I've only discussed the positive G case. So we had this Ising phase up to this absurdly large G of 256. And then we had this gapped twofold phase. And then we have this tricritical Ising transition point, which is supersymmetric. And it turns out that close to this critical point, we're in a gap phase, which is also supersymmetric, because the only relevant interaction that breaks the symmetry here turns out to preserve the supersymmetry. If we go to G over 2 of plus or minus infinity, so T is 0, the positive G and negative G are actually equivalent. But as soon as we turn on T, these are not equivalent. So now let me look at what happens for negative G corresponding to repulsive interactions. So now it turns out that we get 2 transitions. One of them is the Lifshitz transition, which occurs at G over T around minus 0.3, as I recall. And then we get a generalized commensurate and incommensurate transition at G over T around minus 3. So let me analyze these transitions. So there's a remarkable intermediate phase in this region, which is again supersymmetric, but now it has both a gapless complex fermion as well as a gapless Hermitian fermion. So we have a Majorana fermion coexisting with a Dirac fermion in this gapless region. This can be understood from interactions modifying the dispersion relation for the free Majorana model. So a second neighbor hopping term is not allowed by symmetry, but a third neighbor hopping term is allowed. You can see this because of this symmetry. So if we look at a third neighbor hopping term, now we get a sine k and a sine 3k dispersion relation. And as we turn up the third neighbor term, we eventually get this dispersion relation. So now we have Majorana modes at k near 0 and pi, but we also have ordinary Dirac fermions at k0 and minus k0. This k0 depends on interaction strength. So now if we analyze this region where the third neighbor hopping induced by interactions is large enough, we have non-interacting model as coexisting Majorana fermions and Dirac fermions. So we can write down effective interactions. So we have the usual Lettinger-liquid interaction, which will change the Lettinger parameter involving just these complex fermions. But we also have an interaction which couples the Majorana fermions to the complex fermions. But this is turns out for standard Lettinger-liquid interactions, and with the sign of Lettinger parameter that we get from this term, this turns out to be irrelevant. So we can ignore this term. We also have this term, which just involves this involves both the complex fermions and the Majorana fermions. This involves derivatives. As the Lettinger parameter G gets larger, when it gets very large, eventually this will become relevant. This happens when Lettinger parameter gets up to 0.3. But we also have a K0 here, which also varies and will make this interaction irrelevant. So this transition into the C equals 3/2 phase, sorry, the first transition occurs at G equals minus 0.3. This is a Lifshitz transition. And this occurs just from basically changing the third neighbor hopping term. And at G equals minus 0.3, we get third neighbor hopping term changes sign, and we get a Lifshitz transition. Oops. And it turns out that the velocity vanishes at this critical point, as we can see from this diagram. On the other hand, the transition out of the C equals 3/2 phase into the strong coupling broken symmetry phase occurs at G equals minus 3. At this point, K goes to 1/4, and K0 goes to pi/4 simultaneously, so that this interaction becomes relevant. So it's a remarkable kind of commensurate and commensurate transition occurring in this model. Okay, so I'm done. Thank you. I'll take any questions.
Okay, so if anyone has any questions, just please unmute yourself, or you can raise your hand, whatever you want. Yes, Dr. Hooley.
Hi, yeah, so thanks again for a really interesting talk. On that very last point, is it necessary that K0, I'm trying to see why K0 should go to pi/4 at just the same point where the Lettinger parameter.
Yeah, it's a remarkable, we don't have a complete understanding of this. It still probably requires a bit more study, but that's what we found from DMRG, that simultaneously this interaction becomes relevant and stops oscillating at the same point. This is not completely unheard of. This actually occurs in another much more well-studied model. It goes back to work in the 70s by Haldane and Schultz. So they studied just the spinless fermion model with a non-zero chemical potential. And again, they found that there was a transition. So if they fixed the chemical potential, cranked up the interaction strength, they found that they went to a commensurate filling at some critical coupling where there was again a sort of a simultaneous transition. Some interaction became non-oscillating and interaction and relevant at the same point. So this commensurate and commensurate transition was studied by Schultz and Haldane in the 70s. And in this case, they had a more complete understanding about what happened.
Mm-hmm.
So we're finding something very similar is happening in the Majorana model. So remarkably, simultaneously, the interaction becomes relevant and becomes non-oscillating at the same value of interaction strength.
Mm. Yeah, thank you.
Okay, any other questions? So I had 2 questions. So
Okay.
this is on the sort of system you're talking about on this side specifically for the 1D system, correct?
Yeah.
So what do you mean by Lifshitz transition? So
Okay,
I mean,
means
the way
that-
I understand it.
Yeah, there's a well-defined meaning for that. So we're going between, let me show you the phase diagram. So it's this transition here. So, sorry, this transition here, I mean. So both of these phases are relativistic. They both have linear dispersion relations. But at this point, this dispersion relation is cubic. So this is not a Lorentz invariant point. So it's a transition between two Lorentz invariant phases that has a cubic dispersion relation, and this is usually called a Lifshitz transition.
Okay.
And we can understand it at a mean field level, just because the interactions sort of induce a third neighbor hopping. The third neighbor hopping actually leads to a cubic dispersion relation at this critical point. So linear dispersion relation here, two linear dispersion relations here, but a cubic dispersion relation there. And that's called a Lifshitz transition.
Okay. Okay, I see. Thank you. And then the other question I had was, Nat, you mentioned that the superfluid transition point, it's basically equivalent to like a supersymmetric theory. So I'm curious where else, and you mentioned in other areas like condensed matter where we've seen it. So I'm interested in what other systems do we see this in, and what makes the Majorana model special?
Okay, that's a good question. There have been a few papers that have studied this model, obtaining it from square lattice models. But they did not start with Majorana Fermions. They started with ordinary Dirac fermions. And I'm trying to remember that they had, I don't remember details, but I could send you a reference to the paper.
Okay, thank you.
But they studied some models with certain types of interactions that led to this type of interaction in the continuum limit, which not surprisingly preserved U1 symmetry, because in their case, the lattice model preserved U1 symmetry. So they found lattice models that also led to this continuum model. Difference from our model is that the UN symmetry was exact, it was not emergent. I'll send you a reference to the paper. I don't remember details of exactly what the lattice model was. I think it was a square lattice model. I think they had to put in certain symmetries that led to this gapless phase when G was irrelevant, and therefore gapless fermions, and therefore gapless fermions and bosons at the critical point. So they can involve some additional symmetry they imposed, which led to this supersymmetry. I'll have to remind myself of exactly what it was. But it was different because they did not have Majorana Fermions.
Okay.
Good question.
Thank you. Thank you. So any other questions? So maybe I'll wait 5 seconds if anyone wants to unmute themselves. Oh, no, you're still there.
Okay.
I think my internet connection was a little funny. Yeah, so if anyone else has any questions. Okay, so if no one has any more questions, maybe let's thank Professor Affleck again.
Thank you.